Welcome back to Overthinking Tech. Today we're going to be compiling TensorFlow from source. I'm also going to talk about CPU instruction sets, as this is one of the big motivators for why we might want to compile TensorFlow from source. If you don't care about that, use the chapter markers down below to just jump to where I'm compiling TensorFlow. Before we get started, click the subscribe button. According to YouTube Analytics, telling you to subscribe drastically increases the percentage of you that do. So why do we care about instruction sets? Well, chances are, if you've used TensorFlow, you might have seen something that looks like this here. This says, to enable the following instructions, yada yada, rebuild TensorFlow with the appropriate compiler flags. This is why we need to compile TensorFlow from source. It's the only way to rebuild it with these appropriate flags. And there's this long list here of instructions, but it doesn't really tell you what these are, so I'm going to give you a really fast, kinda hand-wavy explanation for this. CPUs have a few dedicated tasks that we can kind of expect all of them to be able to do. These include things like grab data from memory, multiply or add 2 bytes together, or 2 single point numbers, which are actually 4 bytes, or double point numbers, which are 8 bytes. So the most common data sizes that get used for mathematics. And it can add those together, and then it can write that out to memory. And then we can have it do this again. And that's basically all the CPU is doing as we run through code. But that isn't necessarily the most efficient way of doing things, especially if we're working on vectors or matrices. It's much more efficient to just give the CPU an entire vector or 2 entire vectors and say, work on both of these and then give me the result, as opposed to giving it one little piece at a time. That's why instruction sets like AVX exist. AVX stands for Advanced Vector Instructions, or extension. The X stands for extension. Don't think too much about it. This allows a CPU to work on an entire vector all at once, instead of working on each bit of the vector separately, or each number in the vector separately. Now, AVX instructions are fairly new. I think just within the last decade is when we got AVX1, and we've already seen 2 additional extensions to that, being AVX2 and AVX512. This is only supported by x86 CPUs like AMD and Intel CPUs. ARM chips aren't going to be able to do this. So why do we care about being able to do math more efficiently? Well, if we're trying to run really complex code, like a neural net, being able to do math efficiently is exceptionally important. Technically, this is why GPUs are faster. They have tensor cores, which just do this math more efficiently. But we can use our CPU, in some cases, to also do the math more efficiently. Now, running this Python script, right now I'm running this natively inside of Windows. And like we saw with this message up above, I don't have really any good instruction sets working. Not even the basic AVX one, which turns out that first basic one is a really big deal. And we can see that for this neural network here, I'm looking at a training time of like 25 minutes. So what happens if I have all of those instructions? So let's look at what happens if I run this same neural network with all of those instruction sets enabled. First thing to notice is while there's a few pop-ups here, I'm not getting that pop-up about instructions. Second thing to notice, that's not 25 minutes. That's a lot less than 25 minutes. So how did I get to the point of being able to do this way faster? Well, actually, it turns out to be a lot easier than you would think. I did compile TensorFlow from source, and don't worry, I'm still gonna get to that. But as it turns out, if you just do pip install TensorFlow and you're in Linux, it seems to grab AVX for you. You can see here I'm missing instruction sets I wasn't previously missing, but I still have the first of the AVX instruction sets, as well as some of the other SSE instruction sets we saw referenced over here. A few of these guys, which are also very important. Now, in my testing, going from the simple pip install TensorFlow that I used to get this up and running on Linux to running all the instruction sets isn't a huge difference. But let's look at how to compile TensorFlow anyways, and we'll see if there's any difference in the end. Couple of things to get started with. I will be doing this in Windows Subsystem for Linux, just out of convenience. This will work really in any Linux installation. I will be referencing the TensorFlow build from source documentation. And then if you see me copying things from this little notepad down here, this is actually just a notepad with history open because I've already tested to make sure that this works. I will be linking to the build from source documentation. I will also provide a copy of the exact commands I've run, so you can copy and paste. Just check the video description for those. I will also be providing the Python script that I was showing at the beginning, which is what I'm using for testing. It's the same script that I plan to use when testing all GPUs going forward. It took me a little while to get that kind of ready for publication, but it's ready. Also, if you're interested in PyTorch, the only thing I'm really missing for PyTorch testing is I need a neural net in PyTorch that matches the neural net architecture I built in TensorFlow. I'm working on it, but hey, if you can use my TensorFlow and build a PyTorch version, send it to me and I'll add it to testing. Now, if you're following along in WSL, or if you're on a clean Linux install, first thing you're going to want to do is get mini conda set up so that we can create a standalone Python environment. I'm going to include the two commands for that in this script. The first just downloads a file that basically does all the work for you, and the second command runs that file. Once mini conda is set up, we will use conda create, and we are going to create an entirely clean Python environment. I'm going to give this a name. In my case, I'm going to call it pythontemp because I'm probably not going to keep this one. And then we do want to specify the Python version. At the moment, I'm going to be using Python version 3.10. This is compatible with the versions of TensorFlow at the time of recording, which is July 2023. Once we've done that, then we just need to do conda activate and activate that environment. You should see the name next to it here. Now, the first thing we're going to do is we're going to set up a couple of dependencies for TensorFlow. For this, all I'm going to do is copy and paste. And then when I tested this the first time, there was a couple of packages that my system was missing that I needed to install. These are all going to be used when compiling TensorFlow from source. And again, copy and paste this from the document I linked to down in the video description. I'm going to be skipping the install GPU support section. Realistically, if you have a GPU in your system, it's going to be faster than your CPU as long as you can use it. So you really don't need to recompile from source to get CPU extensions. But there are also times where you do need to recompile from source to get some GPUs to work. We'll see later on that we can enable ROCm support during this process. Okay, now to download the TensorFlow source code, all we're going to do is do a standard git clone. Once that's done, we can cd into that TensorFlow folder created. And inside of here, there is a configure file. But what we actually need to do is use Python to run the configure.py right here. And what this basically does is it's a convenient Python script that lets us nicely interact with a configurator that's going to help set up the way this gets compiled. So locations I'm going to leave as the default for both of these. I'm going to say no to ROCm, which is support for specific AMD GPUs. Also no for CUDA. I'm also going to say no to Clang at the moment. This just makes this a little more cross-system compatible to not use Clang, which is also why I skipped that step in the TensorFlow install guide. Now we have the opportunity to specify optimization flags. For this, we are going to use dash march equals native and hit enter. Dash march equals native just tells the system to use all of the extensions that are native to your CPU. No again for Android builds, and we should be done. Now, the next thing we need to do is we need to use bazel build, this right here. But we don't have bazel, and getting it's a little bit funny. So to get bazel, we're going to install basilisk. Well, I always want to call it basilisk. It's basilisk. This is linked to from the install bazel section of TensorFlow. It takes you to a GitHub repo, and what we're going to do is come over here to releases, and we're going to find the newest release. In my case, it's v1.17. And I'm going to grab the Linux AMD 64. Now, depending on if you're using WSL or a dedicated Linux machine, how you get this on the machine is going to vary. Since I'm in WSL, I'm just going to come to my Ubuntu folder, and I am going to put this basilisk-linux-amd64 file that just downloaded right into my home directory. Now, from my home directory, I need to move this to a system path that things can actually find. To do that, I am going to make sure I'm in that home directory, and then I'm going to do sudo move that basilisk file, and I am going to just rename it to bazel while I move it, and I'm moving that to that user local bin so that it shows up to the system as being present. The next thing we need to do is we need to make this file executable. So sudo chmod +x for add executable. And now we should be ready to compile using that bazel command. Now, the TensorFlow documentation gives you kind of a starting point for this bazel build command, but there's a few things that were non-obvious to me the first time I ran this. So you probably just want to copy and paste directly from the document I've included. So what I've included with this is sudo at the beginning. Because of where I put bazel, I found that you need super user permission in order to do this. We're including the build. -J specifies the number of jobs that can run simultaneously. I'm setting this to 12 because I have a 12-core CPU. It will default to however many threads your CPU has. And this is the first place you can get into issue. It will try to use all of your memory and then crash. So I'm limiting it to 12 jobs instead of the 24 it wanted to run by default on my system. And I'm limiting the local RAM to 8 gigabytes. You can set this for whatever you're going to have available in your system. The more cores and the more RAM you can give it, the faster this will go. And this is kind of a slow process. I am also doing --configure equals opt. This is just telling it to use the configuration that we basically just set up. And then I am pointing it at TensorFlow. And actually, it occurs to me that before I can run this, we need to make sure that we are in that TensorFlow folder that was set up. So I'm going to make sure I'm in CD TensorFlow. This is the one that we downloaded when we did the git command. And now I should be able to run this, and it will start building. Now, this is the part that will take a while. As you can see, the total number of jobs keeps climbing. This is also where the system has a tendency to crash if it runs out of memory. If that happens, don't worry. Just run the same command again, decreasing either the amount of RAM that you let it see or the number of jobs until you get it to complete fully. Well, after a long, exhausting coffee break, It's finally done compiling, and you might think we're ready to install TensorFlow. Not quite. We got one more step. So what we actually have done is we've compiled this into something that we can now run, and then we will be able to install TensorFlow. This one ends up being really easy. If you left the configuration on the default, like I did, you'll just copy this single command, paste it in, and remember to include a sudo on there. Now the script is going to give you a warning. Don't be alarmed. All the warning says is that we're going to have to use pip to install this, so don't worry about the warning. Once it finishes, we just need to do a pip install. And if we go off what's here, this is mostly correct. The temp TensorFlow package, that's all going to be the same. The only thing that's going to be different is your version and tags might be different depending on when you compile this. You should only have one option on your system, so if you pre-fill the temp TensorFlow _ package and then just hit tab, you should be good to go. This is going to do a basic installation just like any other pip install. The only difference is instead of going and downloading something, it's installing the package that is now on your system. Once the pip install command is finished, we should be ready to just run our Python script. However, it won't. I don't know if this is going to be everybody's system. My system is specifically looking for a file that it can't find. The solution to this, which I will include in that text document, so again, go copy and paste, is basically to create a link from one location to another. I think the reason that this is needed is there's something that's installed on a system level that it wants to have present inside the conda environment, and it isn't currently present. Now we're going to have to, in this command here, make sure that the name of the conda environment is correct. In my case, that's going to be this pythontemp with an E in there. You'll also need to make sure that like your username and path correctly point to your conda environment. If you're following along, that should just be a matter of changing your username here. Now if we give this a try, we'll be training. So was this worth it? Well, maybe not. I'm going to let this finish out and we're going to get a time for this. Note that we don't have anything telling us about missing packages. So we are running everything including AVX 512. This is a Ryzen 7000 series chip. One of the reasons I bought it was for the AVX 512 support. Compared to running this with just base AVX, we're kind of going to be a horse apiece. We'll see what those exact numbers look like. But compared to what I showed at the beginning, running this in Windows where we have no AVX, no SSE, this is a lot faster. This is like 25 times as fast. So we get a time of 66 seconds. If I run the same script, but in an environment where I have AVX, but not AVX2 or AVX 512, so again, we're missing a couple, but we have the big ones. We have all of the SE as well as the first AVX. And what we'll see here from the time is that we're not very different. So there you have it. It is 3 seconds per epoch faster if you have AVX 512 support. This is something that could change in the future, depending on your exact neural network architecture, how much cache your CPU has, what all the considerations. That 3 seconds might grow. Obviously, there is a huge difference between that and the massively slow half hour that this would take with no SSE and no AVX. So if you're in this case here, I would say it's definitely worth compiling from source. If you liked the video or found it helpful, click the like button. I am still working on getting PyTorch set up, but I'm hoping to have testing for that eventually. I also have some more home lab videos. I know it's been a while since I've done something besides TensorFlow, but I am planning on doing a full step-by-step tutorial for making your own smart speaker, including Spotify Connect and Tidal Connect, for anyone else out there that likes Tidal like I do. So make sure you click that subscribe button so you don't miss any of those.